Hello everyone, how's everyone doing? I'm doing good and hope you're doing good too. Today I'm gonna do a problems called shortest path to visit all node. This is a hard problem, so let's get our hands dirty. You have an interactive connected graph, of course, and of n nodes labeled from 0 to n minus 1. You have a graph, and the graph array right here, meaning that, let's say for node 0 in this graph, this is index 0, index 1, index 2. For node 0 is connect to these number. For index 1, index 0 connect to 1, 2, and 3. Index 1 is connect to 0, node 2 connect to 0, node 3 connect to 0. So it's represented like that. Straightforward problem want us to find the shortest path that visit every single node. As you see in here, from 1 we visit 0 to 2, 2 back to 0, and then 3, and for step 1, 2, 3, 4 for step. And then that means that we need to have some count system. You may start and stop at any node, so we can start at 3 first, or 0 first, 2 first, doesn't matter. You may revisit node multiple times, and you may resume an edge. Alright, so whenever you see shortest path, the first thing you need to come in mind is to use BFS. And then the problem say that we can start and stop at any node. So initially, our queue, BFS using queue, we will contain all the node like 1, 2, 3, and 0, right? We will start with every single node. It's called multiple sort BFS. So we start with many, with all the path that are available. The only hard part is the visit node, right? So let's say in normal BFS, right? We visit, let's say we add 1 right here. We add that 1 to our visit set, right? Then we move on to 0, right? We don't see 0 in here. We add 0 in here, and then we move on to 2. We see there's no 2, so we add 2 in here. But when it is from 2, we want to visit back to 0. That is not allowed because 0 is already in the visit set. That is the hard part of this problem, because since 0 is already in the visit set, we cannot backtrack or traverse back to 0 to visit 3. So we need to have a system to solve this problem, right? So let's start with our visit right here. With the normal visit, we need to add an extra state to define that, hey, we are at let's say we are at 2 right here. To define that, hey, we are at 2 right now, we need to visit 1 again to visit 3. Is there another state in this kind of visit set that determine if I can go back to 0? And that state, what we're gonna use is, it's gonna be a Bitmask, just like that. Let's say we have number here, right? This is represent node, right? So from node, this node is node 0, this node is 1, this node is 2, this node is 3. Let's just mark it down just to make sure that you 1, 2. Oh, my bad. It should be backward. 2 and 3, like that. Let's say we are at 1, right? It means that we visit 1. We add that 1 into our visit node, but we also update this bitmaps, right? So this one now turn to 1. It just meaning that, oh, we visit this node already, but the other one we have not visit yet, right? So we move on to 0 right here. We add that into our visit, and then we update this to 1, just like that. And then we add those into our visit set. Then we move on to 2. Let's say we move on to 2, and we update this to 1. Yep. And then we look back into our visit set. Right now we already visit 0, right? But in our set, let's say we're storing another value in our visit. Before, I think it's 0, 0. From 1 we have 0, 0, 1, 0. From 0 we have 0, 0, 1, 1. From 2 we have 0, 0, something like that. 0 0, oh, not like this, 0 0 1 1, right? So when we holding 0 1 1 1, when we're holding this, right, we're holding the Bitmask like this, and we look on our set, we need to find 0, right? We don't find any of the visit set that have 0 and 0 1 1 1. All right, so we can add that. It's just to here, and then we have 0 1 1 1, right? Just like this. Oh, this is what I mean by having another state, right? This state, it just helps us to keeping track all of the node that we are visit, right? So we are here. It just means that, oh, we are at 0 and we already visit 1 0 and 2. Now we go into 3. We mark this as 1. We add 3 in here, right? And then since we visit 1, it means that we visit all the node, right? When we found this, we return the count immediately. So what is the algorithm for this? Let's say to have this kind of map, right? We just need to, whenever we initially add to our queue, right, we always gonna add the first one. So we add, let's say we are at 1, so we add this to the queue, right? This is our current mask into that, no, not like this, yeah, into that queue, right? To get the current mask, it's just simply 1, and then you left shift it with the number of I. So let's say 1 in here, 1 is like this, right? Let's say I is 1, so we shift it 1, so it should look like this. So this is how we convert it to this. If it's I is 2, we convert it to 1 here, right? So this is how we initially get the map, the mask, current mask, Bitmask. To get the final mask when there's 1, right? There's an algorithm just like this, and then let's say this is 4, right? So we put 4 in here, and then we minus 1. This will return this, 4 of that, right? Or you can do this, I don't know, just like that. That is the whole thing. And then in order to, let's say we are at this run, right? And then let's say we visit 2, to convert that, let's say we are at 0 and 1 right here. So let's remove this. The current bit mask for 0 and 1 is this, right? How to update this mask to 2. Just simply do an OR statement. This statement to 2 is gonna look like this, right? Just look like this. So when we do the OR statement right here, it will make this to this. So that is all of the problem. Let's try to code it up and see. It will be more clear when you code it up. So now let's start with defining something. We have a graph. This n is the count of the node, right? So if n equal to 1, we just return 0. This means there's only one node, so we don't need to count the path for that node. We have a final mask, which is, as I said before, it's all gonna be 1, right? 1. So this one we bitmask that of 1. Then we have our DQ, and we also have our visit set. For I in range, we need to add all of the node into our queue. As I said before, we have the mask, which is 1, shift left I, shift left with the I to get the mask of it. Then we add that bad boys to queue. So we have I, which is the node. We have our mask, and we also need to have our count, which is 0. So let me note this down right here. So I have the node, right, the mask, which is, let's just demonstrate it like this, and the count. Initially count would be 0, right? So visit, I already visit the node and the mask itself, right? Here is where a mask is an extra state, I is a regular node that we visit, but mask right here is our extra state to use to traverse back to from 2 to 0. So this is our BFS normal thing. So we have our node, our current mask, our count, right? Which is q pop left, right? So for neighbor in the graph of our current node. First of all, we need to know our next mask, right? For our next step, which is, as I said, or this current mask or the other mask. So we have current mask plus 1 with our neighbor. Yep. And then if our next mask, right, next mask will equal to the final mask, we'll just return it right away. Return the count plus 1. Yep. We'll just return that right away. And yep, that's just it. I think so. Right. So if my neighbor and my next math is in visit, which means I'm gonna continue. In other case, we need to add that bad boy into our visit neighbor and next mass, and then we also need the queue to append next mass and our count plus 1, something like that. In the end, if we cannot do it, we just return 0. There's no path. Let's try it. Yep, looks like it's worked, and the result is this. Perfect. Thank you for watching and see you on the next video.